Everything all right?
Hello everyone, thank you for joining the seminar. Today we have two speakers. One is first speaker is Nicole Buczkowski. She's a PhD student from University of Nebraska-Lincoln, Nebraska, and her topic is stability of non-local systems. We have another speaker, Christine Vaughan. She's a PhD student from Iowa State University, from Iowa, and her topic is anantropy consistent quadrature-based moment closure for the Vlasov-Poisson system. So our first speaker, Nicole, will proceed now.
All right. Well, thank you for having me. I wanted to acknowledge that this work was done with my advisors, Professor Michael Foss and Professor Petronella Radu, as well as Dr. Mike Parks at Sandia National Lab. NSF intern sort of enabled this formation, and this NSF award partially supported this research. So today we'll look at continuous dependence in the classical setting, and look at a counterexample and the importance of continuous dependence, as well as some background on non-local models, some operators in non-local models, and some analogous properties. And then we'll look at continuous dependence with respect to the forcing, collar, kernel, and nonlinearity in the forcing in the non-local setting. So in partial differential equations, it's pretty hard to find a PDE, solution to a PDE, and it's even rarer to find one in the nonlinear setting. So we'll look at establishing other aspects of our partial differential equations, including Hadamard-Weld posedness, which will include whether or not your solution is unique, whether it exists at all. And then this third condition, this continuous dependence with respect to boundary or initial conditions, or we will actually generalize this idea to look at things like continuous dependence on the forcing term, or we might call that stability, kernel, coefficients, parameters, things in your operators, so on and so forth. So let's look at the actual definition of that. So if we have some different operators acting on our solution U, and we're outputting some forcing, and we have either some collar conditions, or in the case of a time-dependent partial differential equation, maybe you have some initial conditions. In order for our solution to continuously depend on our boundary data, we want to say, okay, if I change my boundary data a little bit, is it going to bound the difference in my solutions above? Because if it doesn't, that's not really a great thing for modeling. We'll talk about that a little bit later. So we'll say we're going to take the difference in our solutions in norm, and we're going to bound it above by maybe some constant in the difference in our boundary conditions, or again, initial conditions if you would rather. And like I said, we can sort of generalize this to have a sort of idea of continuous dependence on this right-hand side, this forcing, or even something in our operator. Maybe there's some parameters in our differential operator that we want to change and look at the change in. And notice in all three of these conditions, if our collar terms are 0 that are different, or our boundary, or our forcing, or operator, we actually get uniqueness, but the converse doesn't necessarily hold. So now let's look at an example where we do not have continuous dependence. So if we have Laplace's equation in 2D, and let's give it some boundary conditions, we can see that the solution here is going to be 0. Now let's look at, again, the same equation. We're going to parameterize it by n, and we're going to have this first boundary condition is going to stay the same, and then we're going to change this boundary condition to be 1 over n sine nx, which if you think about n getting large, sine nx is bounded between 1 and -1, and 1 over n will go to 0. The solution here is given by 1 over n e to the negative root n sine of nx hyperbolic sine ny. Unfortunately, while we change the boundary condition a little bit as n gets really big, this is actually not going to decrease to 0, which is what our other solution was. It's actually going to oscillate and grow pretty rapidly. So we changed our boundary condition a little bit and we got a huge change in our solution, which is not what we want for continuous dependence. So even in this sort of simpler linear problem, continuous dependence isn't guaranteed. So like I said, we should talk about why this is important. So for well-posed systems, we want to, take information from out in the real world, but our measurements are never going to be exact. If you have a measuring stick, you're never going to get exactly the right length. And then if we're inputting that into our model, our solution might be really different. And we don't want that because then it's not modeling the thing that we want to model, that solution. So we want continuous dependence from that. We want it for numerical simulations because we're going to have approximate data and we want our numerical solutions to approximate our exact solutions pretty well. And also if you have, say, some change or variation in your data due to maybe some randomness, you want to be able to quantify your changes in your solutions there as well. So in classical, and some of this we'll look at in non-local as well, the sort of ideas we might use to establish this are sort of aspects of our solution. So if we have some sort of mean value property, maybe we could use that. Some nice inequalities like Poincaré's, Young's inequality, Helder's, Cronval's, particularly if you're looking at ODEs. Energy methods are pretty big for this as well. But let's switch gears and let's talk about non-local models. So since the 1600s, we've been using derivatives in classical mechanics, which is great, but sometimes we want some less differentiability. So then we can use weak solutions, but even weak solutions aren't going to be enough if we have a domain with some rough boundaries like cusps, or if we have a discontinuity. So if you're modeling maybe a plate and there's a crack propagating, even our weak derivatives aren't going to be very helpful there. So then we'll turn to non-local models to model these situations. So what do we mean by non-local versus sort of the classical ideas? So if you think about in derivatives, you're taking a limit, so you're thinking about information at a point. And so now I want to think about information or collectively around a point. So I have our domain omega right here in white. And for each point x, we're going to take information, and I've drawn it in a delta ball around it. It doesn't have to be a ball. It could be some other shape. And that's going to be our horizon for that point. So these are all the points that this point, maybe we'll call it x, sort of sees in a sense. And that's going to happen for any point in your domain omega, including points near the boundary, which will create this sort of non-local boundary around our domain omega, or what we'll actually call it as a collar around our domain that we need to take information from as well. And this has quite a few nice applications. So image processing, sand piling, and then paradynamics, which models fracture. So if here you have a physical experiment of a crack propagating, and in the second set of images, we actually have the simulation that uses paradynamics, which uses non-local models. And this angle of this crack sort of branching off is the same between the experiment and the simulation. And something you can't see very well is the speed of propagation is the same. So this actually does a pretty good job of modeling what we want it to model. So let's actually look at some operators here, since we can't use derivatives anymore. So if we're going to take our solution, our function u, and this alpha is going to take points from omega twice, then we can define our non-local gradient to be u of y minus u of x alpha xy, where if you think about, for example, alpha being 1 over y minus x, then you have something that looks like your difference quotient, which if you think about y getting pretty close to x, you can think about it kind of being like your derivative. And this alpha, you can think about it as sort of recording the interactions between y and x. So for example, if you're in a crowded room, people close to you might have more of an influence on you than people further away. So you might weight people closer to you with a higher value, for example. And then we'll define our non-local Laplacian to be 2. We're going to take the integral, so we're going to be sort of summing up a bunch of points. U of y minus u of x, mu of xy, where if alpha is symmetric, mu is actually alpha squared. If you have the non-local divergence as well, which is sort of outside the scope of this talk. And then as in the classical case, the divergence of the gradient is a Laplacian, and the same thing will follow here. But and again, mu is going to record the interactions between x and y, and it's called our kernel. So next, let's look at a few properties that we have in the non-local case, and these all have classical counterparts. So the first is an elliptic property that we have the mean value like property. So if we have that our kernel is measurable and bounded above by this function and supported on this ball of radius delta naught, then if the non-local Laplacian is 0, we have this weighted mean value theorem. So we're sort of taking the average over the points in some area around us. And of course, mu is supported on ball of radius delta naught. So this is really not over all of your domain and your collar. It's really just the integral over that ball. And so if you think about this sort of in the classical sense, this kind of looks like your mean value theorem there. One nice thing is you might be able to see this is a little bit easier to prove than it is in the classical case, just by sort of setting this equal to 0 and moving some things around. So we have that. Another property we have that is very important in partial differential equations is integration by parts. So the idea of I have 2 derivatives maybe on our function u, and I want to move one over onto v, and then I'm going to have to pay the price of some boundary term. And so here we're not really moving over derivatives in that sense anymore, but we have the non-local Laplacian, kind of like we had the classical Laplacian right here. And we're going to kind of move over a non-local gradient onto v so that I can only have the non-local gradient on u. And it might look like we're not paying the price of that boundary term, but it's actually sort of incorporated into this left-hand side on the collar here. The last sort of corollary or lemma that we're going to kind of want to need is this Poincaré's inequality. So again, if you have u being in AWM P and you have that this domain omega is bounded at least in one direction, you can bound u in LP above by its gradient in LP with some constant out front that depends only on your domain and that value p, as long as u has 0 trace in the boundary. And you can get a similar result, and there are a few different variations of this in the non-local setting, but you can get a very similar result. Again, u has to be 0 on the collar, but u is bounded above in LP by this constant that has only to do with this domain omega and this p. And something that kind of looks like your non-local gradient, you have a sort of specific choice of kernel here, but if this bounds your kernel below, you actually also get that result. So now let's look at the non-local boundary value problem. So we have our non-local Laplacian is equal to some forcing here, and now we're going to have, instead of boundary conditions, we'll have collar conditions. And so these non-local operators, if u is in C4, you actually get that the non-local Laplacian converges to the classical Laplacian at order of delta squared. However, so that means that, of course, if we have continuous dependence in the classical case, then we'll have it in the non-local case if u is also in C4. However, we want these non-local models to work for functions that are not necessarily C4, that maybe don't have any smoothness. So we can look at a few different results there. So we're going to first look at 2 different results with the linear forcing. So this first result, we can get continuous dependence on these solutions, u with regard to the changes in the forcing. and with our constant being to do with our kernel function, our domain and whatever power p we have, 2p here. As long as we meet this condition where this measure of omega to the 1 over 2p mu and LQ norm over mu and L1 norm is less than 1, which basically is going to usually amount to you're going to need your ball of radius delta to be larger than your domain omega, which is fine because you can just make your collar really big. But you get this for all in L, 2p, all of those norms. So let's actually take a look at this theorem, the proof of this, or a sketch of it. So using that mean value-like property that we had before, we can rewrite u as a function of x in this way. And then subtracting the two solutions and taking the LR norm, we can have something that, we've got a nice convolution structure here. We have the term that we want, that f2 minus f1 and LR, and we've got some constants floating around with regard to the kernel. Or sorry, in terms of the kernel. And so let's exploit that convolution structure by using Young's inequality and Helder's inequality to get, something that we're going to subtract over, because we'll have this u2 minus u1 and L2p. That you can sort of start to see that constant coming out, that mu and LQ, mu and L1, measure of omega. So rearranging, we get the desired result. Now, it would be nice to not have that restriction, and we can get a different result using actually sort of same ideas of the usual energy methods. And we'll go through that proof sketch in a moment here. But we can also just get that the u and the solutions are bounded above by that Poincare constant and the difference in the forcing as well. And this is only for L2. So like I said, it kind of follows our usual idea of our energy arguments. So if we take the difference in the non-local Laplacians, because they're a linear operator, we can rewrite that as the non-local Laplacian of u2 minus u1 is equal to the difference in the forcings. So if we multiply each side of this by u2 minus u1 and integrate, so that left-hand side I've written right here. And then, well, we can use our non-local integration by parts, so we can sort of start thinking about moving a non-local gradient over onto this u2 minus u1, and then we'll have non-local gradient in u2 minus u1, so we have two copies of it. And then, well, if we have L2 norm effectively of this non-local gradient, well, non-local Poincare's inequality says that this bounds the norm of the difference in the solutions above, and we have the Poincare constant. So we effectively have that this u2 minus u1 and L2 is bounded above by this term right here, but we know that this is f2 minus f1. And so then using Helder's inequality and then dividing by this spare copy that we have floating around of u2 minus u1 and L2, we have our result. So something that's really nice about this result, other than the fact that we don't need that condition anymore, is this is actually fairly generalizable to the collar argument. So we can get the u2 minus u1 and L2 is bounded above by the norm of the difference in the collar terms. We do carry around more than just the Poincare constant here, but still, if mu is fixed, we have a constant there. As well as we can actually look at the continuous dependence with respect to a kernel, which is effectively changing your operator sum. And this is written for Laplace's equation here, but you can actually get it for Poisson's equation as well. But you do carry around a norm of your forcing term times something that looks like the norm of the difference in the kernels. But you do also get this result for the kernels, and you get for the kernels in L2 and actually in L infinity as well. And lastly, we can get if we have a nonlinearity in the right-hand side, but as long as that nonlinearity is Lipschitz, we can actually also get continuous dependence in this nonlinear problem. using that result, where this constant is the Poincare constant over 1 minus the Poincare constant times the Lipschitz constant of either the forcings, really. So we need this constant to be, of course, greater than or equal to 0, or sorry, greater than 0. So this means that our denominator needs to be larger than 0. So since the Poincare constant actually is fixed based on your kernel, this Lipschitz constant then actually is bounded above by 1 over the Poincare constant, which means you have a bound on how much you're sort of growing or decreasing in this function f. So in the last few minutes of this, let's look at some numerical results. So we use these ideas by Chen and Gunsberger that we can use finite element methods for pair dynamics modeling. So what we're going to do is we're going to, change our forcing or our collar or our kernel in our code, and our code's going to give us back u. So I wrote up two forcing results, and my collaborator Mike Parks actually wrote the codes for these. So if we're going to consider this kernel 3 over 2 delta cubed so that we converge to the classical case supported on our ball of radius delta. So we're going to use this domain omega. So these two things are going to mean that our collar is negative delta to 0 and 1 plus delta. And we're going to look at this forcing. So, and the epsilon is the thing we're going to change. So if you notice when epsilon is 0, that's what actually we're going to use our baseline to compare to for each of these different epsilons. We actually have a nice continuous function. So as you increase epsilon, you're sort of increasing the jump in the discontinuity there. And so here's a sort of table. So here's the different epsilon values that we're comparing to that when the case when epsilon is 0. And here's the difference in the solutions for those different forcings. And so as long as, the norm of the solutions is bounded above by these forcings times the Poincare constant, which for this kernel is 9/4, we should be good to go. And actually, if we go through and we divide all of the norms of the solutions, difference of the solutions over the norms of the difference of the forcings, we get something that's much less than 9/4. So, and actually we get a constant here, though that's not always the case. And so here we have a plot of the different, for the different forcings. So epsilon 0 is in black, and then we're going through the rainbow as we go through epsilon 1, 2, 3, and 4 for these different forcings. So these are different solutions that correspond to those. And so you can actually zoom in a little bit and see the nice continuous one when epsilon was 0 and the jump getting larger and larger in the solutions as well. However, they are staying fairly close together overall. Oh. All right. And then let's sort of look at something that's kind of does the opposite. So we'll keep all of the same kernels. We'll have the same Poincare constant. I don't know why this did this. Okay, there we go. And so we'll look at this forcing, the sort of sigmoid function here. And this time actually as epsilon gets 0, you have a discontinuous function. And so here's the different forcings as we go about, the difference in the forcings, the difference in our solutions again. And again, this is still much less than 9/4, and at first it's sort of increasing, but it seems to be, stabilizing as you go on. And you can see the different functions, solutions u here, and on the right here, we've sort of zoomed in on the where the discontinuity is. So this is at 0.5 right here. And you can see all of the solutions are nice and continuous except for, again, this one where epsilon is 0. But we still have that nice continuous dependence that we want. And so we're trying to follow these up with more numerical tests, particularly in that nonlinear setting, generalizing these for a larger variety of kernels, eliminating some of those restrictions. So that restriction on that Lipschitz constant and the domain and the horizon from that first theorem we looked at. And And then we'll want to look at other nonlinearities. So nonlinearity is sort of inside the non-local Laplacian. Here's a few other papers if you're interested. This one in the middle in particular goes into more on the kernel and changing the horizon and the singularity inside. But thank you.
Thank you so much, Nicole, for your talk.